Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating. Welcome back. We continue our study of Part 10 Creep Assessment. And in this episode 3, we will dive into the definition of creep API definition. We will dive into example 2, setup, the calculations, and the interpretation of the results. API has a very specific definition for creep. Creep is of course, is a very broad topic, and it has to do with dislocation, motion, but let's start off right now with some basics. All materials that API uses are polycrystalline materials. That means that it has a lot of different grain boundaries of different shapes. And inside each of these grains, the structure is uniform, but there are flaws. If you look over here, for example, there's a material that may be a different element in there, or there may be a dislocation, like an interference identification, or there might be, missing items in the crystal, and all those cause dislocation, lead to cause dislocation motion. Dislocation motion, there's a lot of different examples out there, and the one that I'm showing in the diagram is kind of a case of linear dislocation where a flaw moves, say in this example, left or right. And so what happens is that when a material is under stress, and especially at higher temperature, dislocations can travel more easily. And so what happens is these dislocations or these imperfections migrate to the grain boundary void and create voids. Like that's shown in the diagram here. You can see the voids here and here. And basically what happens is this reduces the strain hardening ability of the material. Example 2. Crude heater excursion temperatures. This is an example taken from API. It's 579 part 2, which is the example manual 2009. And it's a pretty interesting problem. So in this case, they want to determine how much damage occurred and to determine the remaining tube life. So the background is that the fired crude heater experienced a temperature excursion for a short duration. The refinery needs to know how much damage occurred so they can understand how the excursion impacts the remaining tube life. And from this information, you can use to determine if the heater will need to be retubed at an upcoming scheduled turnaround, or if the tubes are likely to last even another run. The assessment done in example 2 is a level 1 assessment. And so in this assessment, we would be following the creep service procedures found in paragraph 10.4.2. And each component, like we've done in the last example, must be analyzed separately. So in this example, there are straight tubes, and then there are two bends. we're going to look at only at the straight lengths. The tube bends are located outside the firebox, so only the cylindrical tubes will be analyzed. So if it's outside the firebox, they're cooler. So we consider the tubes to be the worst case. So and another one, for the purposes of this example, we are going to assume that the tubes are adequately supported and that the circumferential pressure stress is the dominant design condition. Start with the table 2.2, the flaw assessment, to evaluate and to make sure that we're covering all of the right elements of this situation. So we have a crude heater. It's a boiler component, horizontal style, cabin style. Tubes are horizontal. Its design is Section 8 Division 1, post 1998. Materials of constructions, SA 335 P22. And the temperatures are here, and because it's a fired heater, it's a matter of operating hours, not cycles of operation. With table 2.2, the bottom part of the table, a few more things here. We've got our design temperatures for equipment are shown. It's not a cyclic service. There is no excessive scale and light thickness loss, so it's not a consideration. There is no, bulging considered, so part 7 will be determined. But in part 10, we have a high temperature excursion inside the firebox. The tube bends are outside the firebox. There was no damage found, so we're not going to be looking at part 12 in this example. And of course, all our environment is we're processing crude. In table 2.2 is location of damage, whether it was internal or external. The damage was near flaws and orientation, and usually this is provided with detailed sketches. In this case, we don't have those elements, but this is something that would be typical in a report. Another one is the environment. Well, internally it's crude. The repair inspection history. This is the first excursion into the temperature range of the component. Placed in the service in 2000, inspections have been performed every 3 years, probably during turnarounds, and no repairs were required. And they want to make a determination of future anticipated operation. Go through our material data. So we've got P22 material, which corresponds to, by definition, a 2.25 chrome 1 moly. We need these properties to continue our example later, because of course, when you add alloys to materials, the properties change. The material's annealed. It's an 8-inch pipe, so therefore the diameter corresponds to 8.625. Schedule 40, there we go. And it's a seamless pipe, so our joint efficiency is 1. We have a unsupported length of 144 inches. And basically, if you want to superimpose that, you just use like beam theory. And if there's any interest in that, we can do a future video and add that to this example. It's a cylindrical shell, so that's important in the calculations. And the future corrosion allowance is 0.1. Inputs, we've arranged data so that it's more easily manageable. We have our pressures haven't changed. They're sitting at 210 psig. Our temperatures, our past operating is 1115 Fahrenheit, and you can see here very clearly what the temperature excursion was. and a past operating history of 131,000 hours of service. And excursion that occurred was 336 hours long. And we're hoping to get to another 43,000 hours out of the unit. Now we're going to dive into looking at the maximum operating temperature, pressure, and service time. So we take the previous data. This hasn't changed, but here's our excursion. So basically what happened was our past operating now has increased to 175,500 hours. And so we're going to be using this information for our level 1 analysis. We continue on with our analysis. We've organized our inside diameter, and as part of the calculation, the nominal thickness, the mechanical supplemental loads. In this case, we leave that out for this example, but that's where you would insert it. You can see the next page where that would go. And the future corrosion allowance, as we said before, that was given. And then we'd calculate TC based on the nominal minus the future corrosion allowance, nominal thickness. And then this is for the radius. And this is the equations you would use for a cylindrical tube. Like before, we use cylindrical shells in the first example 1, we use the same equations again, and in this case we determine the first step is determine the circumferential stresses, and in this case we take the 2016 edition, and there's some I usually just take both of them, and I take the highest one because then it's a very rough calculation, level 1, and so there's two types based on two different conditions, which if you're interested, you can read on section or equation 2C3.3, and but basically you can see that they're almost identical. So we're going to take the highest value. The next one is to look at the longitudinal stress. The previous slide we looked at the circumferential stress, and we use the same equations again, the corresponding ones. And of course, just as we expect, the stresses are half for longitudinal stresses, and that's how we do it. We summarize it taking the maximum values. So we take the circumferential maximum and the longitudinal, and we come up with this value. We can dive into the most interesting part, the analysis. So from our classification of our material earlier, we have a 2 1/4 chrome 1 moly, and it's an annealed material. It's fairly straightforward now to go to figure 10.9 for this material and for our level 1 analysis. Now there's a lot of interesting things that you can see here to give one a quick judgment of where you are on your tube life. So we determined earlier that our stress was 4 KSI, and our long-term operating life without excursion is shown here. We can see that we're over here on our curve, so that means we're somewhere over here for case 1. And so it gives you an idea that you're somewhere between to say 125,000 hours approximately left to go on your unit if there was no excursion cases. So that tells you that your tubes were well underway to the end of life anyways before this excursion happened. It determines your value for your unit. Now, if here's your temperature, your excursion temperature, now what does that tell you? Well, you're off the curve. So that automatically tells you that the level 1 assessment is no longer applicable, because you have to do a more in-depth analysis because these curves are intended for 1200 and less. So let's summarize that. A past case, which is case 1, we basically got 100,000 to 150,000 hours in a life, and we've used 131,000 hours. So we're approaching the end of the service life for these tubes in very general terms. And because in case 2, with that excursion case, we're running over 1200 Fahrenheit. So therefore, we're looking at a more in-depth analysis to determine what we can do with that. And the first thing we're going to look at is what API calls the damage curves. We know from our evaluations earlier that this is considered to be materials considered to be an 2 1/4 chrome 1 moly annealed material. So we would go to table 10.9 and we pull this chart out. Now we calculated the maximum stress to be 4 KSI, and our temperature here is for our case 1, our long-term situation, and we can see our damage rate is shown below at 1.75 to the power 6 per hour. This is case 1. If we continue outward to the second case, where our temperature was higher for our excursion case, we can see a damage rate here of 6.5 to the power e to the minus 5. That's case 2. Step 3, creep damage rate. From the previous slide, we learned that the degradation creep damage rate is shown there, and the past excursion rate is shown there from the damage chart. We had accumulated damage of 175,000 hours. So that tells us that, from our earlier discussions, that approaching the end of the service life of the equipment anyways, and we have a past excursion, that was the period. So we put that together and we have a damage creep rate of 0.31 and a past excursion damage rate of 0.021. So we put that together, those two rates, and we get 0.33. We do our final check and we find out that it fails. That means with a certainty that a level 2 study has to be done. So let's go through our conclusions. First conclusion, the tubes do not pass the level 1 examination. And secondly, further evaluation is required. I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.